and give applause to him, please. Yeah, my name is Dedi Rosadi. I'm from Gajah Mada University, working in statistics program, basically. And in front of you, we already have the last but not least, I think, speakers for our plenary session. Dr. Matthias Templ. Let me give a quick introduction to him, although you can read on the slide, but he's actually graduated from TUIN, Technical University of Vienna, or Vienna University of Technology, and after that he moved to, I cannot read the name of the institute, I mean the university, but it's in Switzerland. I think you have to read it again in front of the other, or the listener, because that, which is in English, is called University of Applied Science, in German, something like that. Okay. And yeah, he's doing actually a lot of research on statistical computing, yeah, including multivariate and spatial statistics. And the last publication, I think, this is not the latest, I think. He has a books on with the college, also from Austria, and also another one is Karl Haron from, I think, yeah, it's a book on compositional data analysis using R, which is not listed there, but yeah, this I think only on maybe in journals. There is a paper on CODA also in some conference, in our user meeting, in European user meeting, and also in Euros 2017. But I think for today's presentation, maybe it's more on compositional time series, or compositional data, I could say, and many things related to that subject. Okay, please I give the time to Matthias Templ. Time is yours. It's about maybe 35 minutes maximum, I could say.
So thanks a lot for inviting me, and thanks a lot for Dedi Rosadi from UGM for his hospitality and for joint research. So I come from the Zurich University of Applied Science. I'm there since 3 years. Before I was in the Vienna University of Technology, and today you will hear something about compositional data. Maybe you didn't hear it until now, but in your everyday life you have a lot of compositional data. For example, your household have expenditures on food, housing, and so on. And if in 1 month you spend much more on food, you have automatically less money available for other things. Or the time during a day, so your day has 24 hours. If you sleep on a day much longer, say 12 hours, you have much less time available for other activities. So you see there's an inner relationship in the data. Maybe another example, for instance, the Mexican people like to drink margarita, that consists of tequila, of orange juice and triple sec, and only the mixing of these 3 ingredients defines the taste, not the amount itself, so the mixing. So the ratios are important. And whenever ratios are important, we speak about compositional data analysis. So I give you some examples that you can imagine what compositional data are, and that you will see that basically you have compositional data everywhere. There is a solution how to work with compositional data. So if you apply standard statistical methods on compositional data, you get arbitrary results and wrong conclusions. So you have to do a so-called log ratio analysis. I will show you one example with Ph.D. data, so from Ph.D. students' data, and one larger example about probability density functions. That's a little bit more complicated example, and since we run a little bit out of time, I will not have time to get fully into that example, but you will see what you can bring from the last more complicated example, that compositional data analysis is something which is important and which improves your results if you have compositional data. Oops. So in former times, this compositional data analysis group was a small group in Spain, I would say. They've defined compositions, which observations which sum up to a constant, like 1 or 100. And they have many applications in geochemistry. But nowadays, we have a more modern way to formulate compositional data, I would say. That's just quantitative representations of parts of a whole. So your times on some activities during a day, for example. And the whole is the whole day. Whereas the information on the whole, but the information on the whole is irrelevant for us. So that's compositional data, multivariate data, and only the relative information is important. As I said before, for the margarita, the taste of the margarita depends only on the mixing of the ratios between the variables. Units are typically expressed, for instance, for geochemistry data in parts per million, milligram per kilogram, but also for the expenditure data, for example, or the wage data in euro, dollar, or something else, or hours of a day, and so on. Surprisingly, a lot of data sets in economy, in socioeconomics, in biology, in geoscience, in genetics, and so on are compositional, but nobody knows. And the important thing is, if you apply now a compositional data analysis, it's important how to express the data. If the absolute information is given, so the raw data, if we express the data as percentages or as ratios, we obtain the same results if we do a compositional data analysis. Oh, I have a German thing. So we have a lot of different kinds of, in different research fields, composition data, like in geochemistry, but also contingency tables, probability tables are compositional because they sum up, probability sum up, cells sum up to 1. Mortality data, basket data, hours of a day, distribution of species in a certain region, tax, wage, or expenditure data, poll data are compositional data, sequencing data and genetics, chemical components, and even density functions are compositional because the integral over the density function is 1. So I give you a very abstract example now. Here you see a picture of Piet Mondrian. Dutch people know him very well. So for this composition with red, blue, and yellow, he took, I think, more than 10 years to have, for him, the best, let's say, ratios between blue, yellow, red, and white here. And we stored it areas just as a vector. We see, for example, the first is 1 divided by 15 large, the second would be 1 divided by 13, and so on. So a simplified version, we don't store the geographical information here. And the sum is 1. If we would now increase one element, for example, this area, automatically we have less space for the other colors, for the other areas. So you see again, it's an inner relationship in the data, and we have to deal with that. Another example of compositional data, for example, the age distribution on certain age categories, percentages, for instance, Indonesia, you have not many old people compared to Switzerland here, so that's also compositional data. Another thing would be the consumption alcoholics. So in Indonesia, if people drink alcohol, they drink beer. In Switzerland, for example, that's a little bit in opposition, they rather like wine, and so on. That's also compositional data. Actually, they also sum up to 1. Another type of compositional data are coming from geochemistry, for example, the parts per million, from different chemical elements, for example, aluminium, barium, arsenic, barium, and so on. That's typically compositional data. Also poll data, for example from Germany for different regions, the amount, so the political parties, how many votes they had, that's compositional data. Or some tables, or you can produce tables here, magnitude tables. For instance, for each country, you have another dimension, gender, age, and the contract, and the corresponding value. Or, as said before, household expenditure data, for example, expenditures on food, alcohol, clothing, housing, furnishing, and so on. That's also compositional data. Or something from several countries, how much they spend on agriculture, manufacture, construction, and so on. Just to see that there's many different compositional data sets around, and this is a very incomplete list. For example, also contingency tables like here, precipitation in Girona, Spain, 2006. You see there how many days or how many times they have low precipitation until high precipitation divided by spring, autumn, summer, autumn, and winter. So there are some requirements. If you apply standard statistical methods, these requirements are not fulfilled. Some requirements are, for instance, scale invariance. If you multiply one observation in your data set with a constant, the results of your multivariate analysis should not change, because the ratios still are the same if you multiply the whole observation, and only the ratios are important. Permutation invariance, we can reorder the parts, the variables, and the result should not change. Something which we call subcompositional coherence, divided by two topics here, dominance. So the distance between two whole compositions should be larger than the distance between, if you only consider subcompositions, not all variables, but only subs. And this is also violated when you use Euclidean distances and traditional statistics analysis. And something called ratio preserving. Non-selected variables have no influence on the results. We will see an example then afterwards. So another compositional data set, this is a toy example. We see expenditures on housing, foodstuff, transport, and communication. And we see if we express it in absolute numbers or in percentages, the ratios are the same. For example, 1,710 divided by 570 is exactly 3. But if you express the data in percentages, that's the same. So we should get the same results also if we analyze this data or we analyze the percentages. So if you report your numbers here in dollars or in rupees or in euros, doesn't matter. The result should be the same. But is this data set really compositional? Depending what you're doing. If you are just interested on the wealth, maybe it's not compositional. You're just interested on the absolute numbers. If you're interested on the ratios between parts, then the data set is compositional. And what we do in practice, we analyze log ratios instead of ratios because it has some benefits. For instance, a perfect balance. If two compositions have the same value, we have a balance of 0 if we took the log. So an example from before, this consumption of beer, wine, and spirituous behaviors in countries. And what you see here, this is three-dimensional data. I just plotted 2 dimensions. And what we see here, there's no data point in this area. It cannot be because it's constrained to 1 or to 100. So if you have more than 100%, is not possible. Yeah? But you can imagine the correlation is then always negative, forced to be negative. So the correlation makes no sense. You also see that you are in some kind of distorted space because here no points are possible. So in such distorted space, you have to deal with that. So if you apply their standard statistical methods or standard analysis methods, you get arbitrary results. Euclidean distance is not appropriate for that. I give you one of two examples now. One is from Ph.D., number of Ph.D. students in some countries. And you see mostly European countries, but also Japan and US. So the total number of Ph.D. students, and then divided by male and female, and technicians, socio-economic law, human health, and agriculture. And if we just consider the absolute numbers, this has not much information included. So if we just visualize technicians against health, of course the correlation is positive, because it's just driven by the large countries, US, Japan, UK, and so on. So it's not very informative. The more interesting information is between the ratios. Has a country more technicians in comparison to other studies, for example? So that's the reason why the data are often constrained, for example, normalized to 1 or 100. And if you do that, if you show now the number of PhD students in health science and in technical science, now we see this picture. Sweden, for example, is here, Japan is here. But, and now it's the important thing, if we don't measure, for example, one variable, and we express the data again in percentages, for example, we didn't measure socio-economic and law students, you get a different correlation between the variables. So you see, correlation doesn't make any sense if you work with percentages, for example. So we have to find another theory, and the theory is about compositional data analysis. There's a book containing 13 chapters, including compositional data analysis applied for cluster analysis, discriminant analysis, principal component analysis, regression analysis, and so on. So all these methods are there included. It's an introductory book about compositional data analysis and log ratio analysis. In the following, we consider an example which is not in the book, which is a little bit more specialized. I thought probability density functions are more known here in the audience. So I will speak first about functional data analysis and probability density functions. What is functional data analysis? So if you have observations, if you have samples, whereby each data point is a random curve, so it's a function. Probability density functions, of course, are somehow a part of functional data analysis and are compositional, so the integral over this probability density function is 1. And if xi is the ith observation at time t with continuous support in a certain interval, so that's the notation, just a notation, and this functional notation with this continuous is just conceptual, because in practice we have discrete measurements. So we have measurements on points t1 to tn. So the first step of an analysis is therefore always to go from discrete data to curves to functions. That's the reason why it's called functional data analysis. And most popular in functional data analysis is functional principal component analysis for dimension reduction purposes. So we want to analyze, we have maybe 100-dimensional data or 1,000-dimensional data. We want to analyze the data so we want to reduce the number of dimensions with some constraints. The aim is to analyze it in 2 dimensions, for example, to get most out of it. So I give you a motivating example. Here it's my home regions. This is in Upper Austria. So we have population data in 57 municipalities, 19 age groups, and gender. And you will see here there's Linz-Land, for example. Here I'm born. So it's data from my hometown, home region. And if we plot just these 57 population counts for each age, we get these curves. So that's not very informative curves, because we just know that's the capital. That's the curve of Linz. Of course, we have higher counts in the capital. like you would have Jakarta here. So, how we can express this differently? We want to analyze the age distribution, not the absolute numbers. So what people typically do, they estimate 1 or 2 indicators or 3 indicators, but not the whole age distribution, what we just saw. So they estimate, for example, the total number of population size in one municipality. Or they calculate something else, but not analyzing the whole age distribution and comparing each to each other. So what if we do that? So first idea, we use ratios, the relative information between the counts, between the curves, what you saw, and we apply that for each municipality, so the counts per age class divided by the total population counts. What you see here now is the ratios, so we divide it by the sum of the population count, each value is divided by the sum. So you see that's not continuous curves. So we still have to do something. But these are already almost density functions. Yeah. So in the next step, we will obtain density function out of these curves. And we still don't know how to compare these curves here. So what's the goal? We analyze the densities of the age distribution after dimension reduction. And with the dimension reduction, we use so-called principal component analysis. The first component explains the most of the data. The second component explains the second most. That's the direction which explains the second most, I would say, simplified version. So densities, we know that integrates to 1, consists only relative information, and now there are some problems if you apply this standard functional data analysis to these data, to these problems. So in the standard way, if we summate 2 densities, the result is not the density. If we multiply a density, the result is not the density. Even with functional principal components, we will see that we can have negative estimates of density values. That is not very nice to have. And in addition, if we have a density value of 0.05 and another one with 0.01, that's doubling. But if you have a value of 0.05 and 0.055, that's just 1 times 1 larger, but the Euclidean distance is the same as before. So again, Euclidean distances are not very appropriate for this problem. What are the solutions? The solutions are, from the mathematics point of view, rather complicated. I will only give you a brief sketch about that. So we do a compositional data analysis with a log ratio analysis approach. We use so-called Bayes Hilbert spaces instead of Lebesgue standard spaces for integrable functions. And we can define their norm, an inner product, an addition, we call it perturbation, multiplication, we call it powering here in that context, that we can define also for these Bayes spaces. So with this addition, also with the perturbation of 2 densities, again we result a density. And if we multiply a density, we again results in a density. That's some advantages we have. And there's an isomorphism, so we have an isometric log ratio transformation between the Bayes space and the Lebesgue standard space for integrable function. And we can go back and forth there. So that's the something addition multiplication in the Bayes space. So you see here, if we add together 2 densities, or if we multiply a density by a scalar, by a constant, we achieve that. You see this normalization here with the integral. That's the important step. So we consider only ratios here again in this space. And if we do now, if we add f and g together, we again get the density, but in the standard space, in the Lebesgue space, we didn't receive a density at all. If we multiply a density with a constant, we again achieve a density in the compositional sense, but we didn't achieve a density in the standard Lebesgue space. So the first step in the FDA is smoothing. How to do smoothing? There's many possibilities how to smooth data points. In practice, it's always often done using natural cubic splines between all knots with some constraints. You have to define the knots first, and then between all the knots, we fit some polygons of third kind to each with some constraints. And we come to this B-splines approaches here. So if we do that, for instance, for this data set, this is one data from one municipality, the age distribution, where we have the measurements, and we fit the curve then by smoothing. So for all these, within these knots, we fit a polynomial of a third kind with some constraints that we have smoothness also on the knots itself. And that we do for all data, for all observations, for all 57 observations, and we end up in curves. Okay, I think I have to quickly go to over these steps. So principal component analysis, if you have, for instance, 100-dimensional variables, we want to have the first principal component in that direction in the space where we explain most of the variance of the data. And the second principal component will be orthogonal to the first one, with again the same maximization that we again want to maximize the variance of the rest of the data set. So we have this orthogonality condition. The output is some eigenfunction of the covariance and some scores. So the scores representing the observations and the eigenfunction describing the variables here. And interpretation is then not done in the 100-dimensional space if you have 100-dimensional data, but only in k dimension, for instance, in 2 dimension. So we formulated this functional principal component analysis with the compositional approach. It's a new formalization. The maximization steps, there's a trick behind that. You first apply log ratio. We obtain log ratio coordinates. How we do that? Each value is divided by the geometric mean of the observation, and we took then the log of it. So it's called centered log ratio transformation, and we can show, and we proved that is equivalent to be in the base space. And if we do this centered log ratio transformation, we can do this principal component analysis in the centered log ratio coordinates, and we're happy then. So one example here, we have 100 density simulated from a gamma distribution. So it's basically a 100-dimensional data set on time t. And how to present that in 2 dimensions. So we have 100-dimensional data here. How to present that? We use principal component analysis. Here with the classical approach, functional principal component analysis. And what we see here, the first principal component explains 62%. The second principal component explains 28% of the variation in the data set. That's quite high. But we see some nonlinearities in the scores. The obtained scores, and if we compare that now with our approach, with SFPCA, with the compositional approach, we see the percentage of explained variability is much higher from the first principal component, and together we have much more explained variability. It doesn't look any longer strange, and if we use now the principal components to reconstruct our data set, so we just use the first 2 principal components to reconstruct our densities. What we get here with FPC, we get even negative density values here. And if you compare that, you see that's not the same anymore. But if we do that with our approach, we see we basically get the same information. So we can reconstruct just from 2 principal components our original data. So last example here applied to the population data from Upper Austria. So we want to characterize the main variability in population densities from each of the 57 municipalities, the age counts. We are interested to compare them. And we can show that we have much better results now with this FPCA than with the classical approaches. So just in short, we see here the explained variance. The first principal component explains about 80% of the variation in our data, the second about 10. And what we see here from the harmonics, the first principal components explains differentiates between young people and very old people. I think red is female and blue is male. And from the second principal components also contrasts, so people who are 70 until 90 years old to the rest of the age. We get some scores, and I don't want to go into detail here, but if maybe we see here a region called Gmunden that has high score on the first principal component and negative score on the second principal component. So high score on the first principal component means old ages. Negative score on the second principal component means also a old age, basically, compared to the rest of the age distribution. And if you look at maps, and that's already LISA maps, so it's simplified maps. Red, you get the red if you have a high value on the scores and also the surrounding areas are high. Then you get the red. An area is blue if you have a low score, a very low score, and also the surrounding area has low scores. And what you see here, again, this Gmunden, what we saw just before, in that area, the age of people is also of high ages relatively to the whole age distribution in these regions. So young people's young family moved somewhere away from this region. And what we see here around Linz, so many young families moved there. We can interpret that just by looking at the scores in the first two principal components. We would see that just young families moved there. Also for the second principal component, we see similar pictures. We see an area here. So way too much old people live here. So that's contrast. The second principal component contrasts the 69 old to 79 old people or something to the rest of the ages. And we see that the scores are very high here, so we have a very low here, which means there are many old people here. In opposition, there's many young people here for the females and for the males here. You see that structure here is the highway in Austria. So along the highway, there is a lot of jobs there. It's an industrial area. So many young people moved there, partly from this region here. So if you want to search for, especially if you compare that for males and females, we have other maps here where you see if you want to search for your female, you should go in the area around Linz and not to live in Gmunden because there are not much. So the conclusion, what you see, there's many data sets which are compositional. And be aware, whenever you have compositional data, don't apply any analysis on that data without any, so if you just apply it without anything in mind with compositional data, you will get arbitrary results, you will get wrong conclusions. You will get better results if you apply compositional data analysis methods. That's mostly a suitable log ratio transformation, and you analyze then the log ratios instead of the original values. What you saw already with this functional, with the probability density function and the functional data analysis, this was a very specialized problem now, but it solves. So it gives us a great opportunity to deeply analyze the age distribution in a country, for example. So this successful application of this log ratio analysis is in the, for example, in the book, but there is, of course, other books as well available. Yeah, that's basically all. So if you're interested in compositional data analysis, just write me or my colleagues. We are interested to enhance the group of compositional data analysis people. Thank you very much for your attention.
Okay, thank you, Matthias, for a very interesting talk and lecture about compositional data. I think we should highlight the last slide or last line of the slide. If you are using traditional method for compositional data, then you get wrong the result or wrong conclusion with your analysis. So this is very important to know. And yeah, I think because of the time, maybe we just I can give only one question, I mean open question for you if you like. Please ask one question only. There's something you want to discuss, or you can discuss it later maybe during the lunch. What is the best? One comment or question, please. Yeah? You, Deepa? Professor? No? Okay, sorry. Oh, one, okay, over there. One question only, please.
Thank you, professors, Prof. Teddy. Yes, I read the last sentence and agree. That's why now my research moved to the fuzzy numbers, because when we deal with the crisp numbers, we also have problems. In your case, rather than you use a Lebesgue space, you use bias space in order to find, in order to search for another conclusion. And you come into a kind of a statement that the traditional ones should be reconsidered to get the true truth. And if, is there any chance if other people come not using bias but the other measure, other space, is it possible? So they will claim your approach now might also result in arbitrary and wrong conclusions. Is it possible? Thank you.
If I understand the question correct, the question was, we used here base spaces for these density functions. Is there also a possibility to have another space? Yeah. So what we showed.
No, that's why I ask. In my case, rather than use crisp numbers for data, I use fuzzy numbers because in order to find the truth. So in your case, you change the space. So is it possible if other people come with other space and it will claim the same sentence as yours?
So for this application on the probability density functions and functional data analysis, the base space is the appropriate space. So I'm not aware that some other solutions are possible, because you have to normalize through the integral of f and g. To have the data, or the representation, the space should be somehow deal with relative information. So I'm not sure. But for other problems, yes. Yeah. For other problems, you have different opportunities, like you.
Okay. So as long as the PDF assumptions is satisfied, so there's no matter the space we use. So because the
yeah, I mean, you can continue maybe the discussion later, please. Yeah, because our time is already past. I mean, yeah, the organizer already asked me to stop the discussion. Okay, you can continue later, please. Okay, I think that's the end of our session today. Thank you for your attention, and give a big applause to the last presenter, Matthias Templ. Okay, give time to the Master of Ceremony.
Thank you very much to our moderator, Professor Dedi Rosadi, for leading the interesting discussion between the honorable speaker and all the participants.
To our honorable speaker, Dr. Matthias Templ, and our moderator, Professor Dedi Rosadi, please stay. Now I would like to invite Dr. Irwan Endrayanto as the steering committee of the 8th SEAMS-UGM 2019 to come to the stage and pass on the souvenir and the certificate to our honorable speaker and the moderator.
Please give a big applause to our speaker.
And once applause to our moderator. This is the last plenary lecture. Thank you very much to our speaker, Dr. Matthias Templ from Zurich University of Applied Science, Switzerland, and our moderator, Professor Dedi Rosadi from Universitas Gadjah Mada.
Also, I would like to send many thanks to all honorable speakers, invited lecturers, and respectable moderators of the international conference since day one. It is an honor for us to have great discussion with you.
On behalf of the organizers, we do hope that this conference provide a forum for researchers, lecturers, educators, and students to exchange ideas, to communicate and discuss research findings and new advances in mathematics in the wide area.
Ladies and gentlemen, this is the end of our session.
We will continue to the parallel session and mathematical meeting for teachers after break, and the last agenda is closing. Please be informed that the closing ceremony will be held in this hall at 4:30 p.m.
After this, we would like to invite all participants to enjoy your luncheon we've specially prepared for you in the ground floor.
We will commence our next session at 1 p.m. Thank you very much. Information to all participants that the mathematical meeting for teachers will be conducted in this ballroom at 1 p.m. You may enjoy your luncheon first in the ground floor.
Diumumkan sekali lagi kepada peserta SEAMS Universitas Gadjah Mada 2019 bahwa sesi pertemuan matematika dengan para guru akan dilaksanakan secara terbuka di ruangan ballroom ini dengan berbahasa Indonesia. Adapun sesi paralel akan dilaksanakan di lantai dasar sebagaimana tempat makan siang. Terima kasih.